Hello, it is a pleasure to be here today and to tell you how not to train your hackbot. This topic is very hot this year, and we're excited to talk to you about our research on this topic. So if you've been paying attention to the news, you might have noticed that either one of these two things is true. Either ChatGPT has enabled low-skilled actors to do bad stuff, or it is totally useless. The truth is somewhere in the middle, and we're here to tell you where that is. As an introduction, my name is Herbert-Voss. I'm an LLM OG in that I've been working with LLMs for the past 5 years. I was the first security researcher at OpenAI, and I worked on GPT-3 and on Codex. With me, I've got Shane Caldwell, who is also a longtime AI for Offense guy. We're from Run Civil, which is a place where we build and use models to automate hacker intuition, and we're excited to share our research with you here today. In this talk, we're going to be talking through how do large language models work with a focus on features and limitations that are relevant to the security domain. And we'll also be applying language models to offensive security in the context of bug bounty. So what is a GPT? Well, it stands for a generative pre-trained transformer. And transformers are large models that are deep learning models originally designed to generate text. If you're familiar with using AI in the context of information security, you'll probably be familiar with the context of training these models for malware classification as a classic example of discriminative models. Transformers are different because they generate rather than discriminate the samples that you generate from. A good model for thinking about them is as an adaptive lookup table or a compressed representation of the training data that you've been training on. The lookup occurs when you ask the model to predict the next word in a sequence. The first context in which you might have encountered a transformer is actually in your phone keyboard, where you type out a sentence and then it spits out some word that assumes you want to type next. When we say words, we actually are referring to tokens, which are integers that represent parts of words. LLMs are just fancy lookup tables for the tokens, and during training, that's when we're building this lookup table. We create this table by creating dynamic key-value pairs for each input token by generating these key, query, and value token vectors for every position in the input token sequence. We then compute the similarity between these vectors, and this is how you get the attention weights. So if you've heard people talk about downloading the llama weights, for example, these are the weights that we're talking about. You can think about the weights as being a compressed representation of input data that we then sample from in order to complete an input sequence. So how do you get from building a lookup table to solving math equations and other advanced reasoning capabilities? You might be thinking, Ari, surely there's more going on here than simply predicting the next word in a sequence. But no, that's really all it is. Broadly speaking, this particular paradigm is called few-shot learning. And it's called few-shot because you don't really need a lot of examples. You start with a base model, you give it a few examples through an input sequence, and then you ask to predict the next token as an output sequence. So we got an example here of a sentence that says, translate from hex to des to A to what? And we're going to predict what. It's been colorized because it's been tokenized. So you can see these little integer numbers underneath each one of these things. Those are the tokens that we're talking about. So for humans, throughout our lifetime, we've seen enough data to learn how to read and make connections between concepts. So somebody can ask you a question like perform a mathematical calculation. And using what you know about the meaning of translate, hex, and des, you can infer that you need to transform one sequence into another sequence. I didn't need to tell you mathematically which operations to do because you already have enough information implicitly because you've been looking at this kind of stuff for a long time. As hackers, we've seen enough examples of hexadecimal and read enough Hitchhiker's Guide to the Galaxy to know that 2A translates to 42 in decimal. If you've heard of prompting an LLM, this is what few-shot learning is. It's also called in-context learning. You provide the model with a pattern of text that you'd like it to complete, and then you ask it to then generate some text. This little red window here is what we call the context window, which is where you shove the text that you'd like the model to complete. You can put anything in here, and if the model has seen a similar pattern, then usually it'll complete something that's very similar. A good example of this is with the ubiquitous chat interfaces. Chat interfaces are built by loading up a script between a user and an assistant, and then asking the model to then just continue that play. Generating a completion involves the model mimicking how it has seen similar scripts play out. And later in the talk, we'll talk about how when you craft prompts, that has a significant impact on what you can get models to do. It's worth also talking about context windows in a little bit more detail. So if you're going to be doing some prompt engineering, it's also good to know how much you can actually shove into that context window. You don't want to be in a position where you've run over the token limit and are expecting the model to use information that it doesn't actually have. So we've seen over the last 2 years or so that context windows have gotten much bigger. So looking at GPT 3.5 and comparing it to GPT 4, you see a context window growth from 2K to 32K. And then in the case of Claude, Anthropic's model, you go from 4K to 100K. And even in the context of some of these open source models that we're seeing more frequently, we're going from 2 to 4K, which for an open source model is actually reasonably significant. You might be thinking, well, infinite context window sounds great. Like you can just, put everything in it and then ask it a bunch of questions and it'll answer everything for you, which unfortunately there is no free lunch. There never is in machine learning. So in the context of long context, there's just more to forget. So there are also these primacy and recency effects that you also see in human memory. So here I've got a screenshot of a paper that came out about 2 months ago where they took the GPT 3.5 turbo models and they shoved a bunch of documents into it, and then they ran some experiments to see how easy it was to extract certain things from certain parts of the context. And as you can see, at the first part of the context, it does a reasonably good job of extracting stuff or returning things that are what the researchers asked for. And then for the latter part of the context, you can see it also kind of does the same thing, but in the middle, it doesn't perform very well at all. So what do you do when you have too much data and it can't actually fit in like a prompt context window? Well, there's a couple things. So the most obvious thing, of course, is to use the biggest model, but think clearly about what is it that's going to be in the middle of the context versus like the first and the last part. The second thing, which I'm a big fan of, is using vector databases, where you can embed all the documents that you're planning on searching over or using in some sort of context. And then you just do a vector search and find the closest entries that are relevant to what your query is, and then just shove those into context, and then it usually improves the performance. You can also, in the same vein, use a search engine for this information retrieval task, where you just simply have the model use a search engine as a tool, call out to that search engine, grab the information you need, and then just shove it back into context. Over time, we've seen everything get better, not just context windows. So here we have a handy guide for the publicly disclosed parameter sizes. LLM performance improves smoothly as we increase the model size, dataset size, and compute used for training. And we call this the scaling laws. So they're the empirical governing principles for performance. And for optimal performance, all these things need to be dialed in. I will also note that parameter count has turned out to be more complicated than simply more equals better. And there are some tuning tricks that you can do to get similar performance out of smaller parameter models just by doing some crazy training things. So those things being, well, first off, there are 3 ways in which you can get information into a language model. First, of course, being pre-training, where you're just training your own model from scratch. Second, being fine-tuning, where you take somebody else's weights and then you take your own proprietary data set, you fine-tune by, or you train on that same data set with the same weights that you've got, and then it just injects the information from that training set into the model. And then the third way, which is the sexiest way and the way that a lot of interesting things have been coming about now, is with reinforcement learning with human feedback, which is, roughly speaking, you train a second model to recognize when an answer is good or bad, and then you use that as a learning signal to improve the base model performance. So if you use ChatGPT, you'll notice that it feels like you're talking to an agent more so than some of the other models. This is because it's what we call an IF model, or an instruction following model, which means that it's been tuned via RLHF to have responses that mimic a conversation script. And the model's been given enough examples of what a good conversation script looks like that it has a good sense of like what the responses should look like when you ask it questions. So now that we've got a sense of how LLMs work, let's answer this following question. And when you see a titillating headline like this, you just know the answer is no, so let's go through why not. So there are 3 core roadblocks in AI development that need to be overcome for this to be a real concern. So there's statefulness, hallucination, and contamination. Statefulness refers to the ability to store and run things on program states. So LLMs use large amounts of data to predict the next token in a sequence. That's all they're doing. There are promising advances with the information retrieval stuff, but it's meant to augment the sequence prediction accuracy rather than to replace the paradigm entirely. Memory corruption issues are the root cause for roughly 70% of vulnerabilities. And this is stuff like use after freeze, buffer overflows, race conditions, all things that in order to exploit, you need to know something about the program state on the machine and be able to use it. But LLMs don't have memory, so they're not really capable of doing that. A great example of LLMs struggling with this statefulness problem is actually with Mark Dowd's crack adder overflow bug. So I'm not going to go through this in detail, but this is Halvar's reimplementation of the bug in this tiny little window here. The high-level overview is that the code contains an implicit state machine with at least 8 different possible paths, and that requires looping 9 times to get to an invalid state. This means that in order for an LLM to find this problem, it would need to be able to model what is happening as variables update through the program flow. But models, they don't run code, and they're not tracking variables. They are just predicting the next token. So the pattern might exist in the training data set, but that doesn't mean that it's going to be able to actually find vulnerabilities around this kind of stuff. The second thing being, for why GPTs suck at being vulnerability hunters, is the hallucination problem, which if you've been playing with these models, you're familiar with. Like, sometimes it'll just spit stuff out that's not actually true. Hallucinations are predictions that appear correct at first, but are factually incorrect or are entirely incoherent. Making up fake logic or design flaws isn't useful for vulnerability discovery. It could be useful for things like generating fuzz harnesses and stuff like that, but for the actual vulnerability finding step, it's a direct hindrance. In many of our experiments adapting LLMs to find vulnerabilities for source code, we found that it was common for the model to hallucinate variables that just didn't exist, which means you'd have to go through and figure out like which of these things are real, which ones are not. And so if you're already in the weeds with a piece of code trying to find something, having to then double check what your tool is telling you to make sure that it's not just lying to you adds additional cognitive load, and it becomes a non-starter. The third thing that would need to be overcome for LLMs to be good at hunting is this contamination issue. So contamination refers to the training set containing examples of the thing on which we were evaluating. So somebody had ChatGPT take the bar exam. Fun fact, the bar exam questions are in fact in the training data set. So no surprise, it actually does pretty well. But it turns out when you adjust the questions just a little bit, the performance drops pretty significantly. And guess what most LLM training sets include in terms of code? Like, because of GitHub, they contain bug reports, they contain POCs, it contains tool code. This is actually pretty good for stuff like pattern matching for existing vulnerabilities. Like, there are actually some pretty cool uses of LLMs for code analysis, and I'm reasonably optimistic that some parts of the process for doing analysis can be automated, but it's not an end-to-end thing. It doesn't help with finding things that are out of distribution, and contamination actually makes it really difficult to evaluate the baseline capabilities in general. So if you're an ML OG, you're familiar with the rule that you can't test on training data, but this is extremely difficult with transformers because, as I mentioned with the chonk chart, more data, more parameters, everything, you get better and better performance when you have more data. So there's a direct perverse incentive here to train on as much as possible, which also includes things that you might want to be evaluating on. If you feed the crack adder vulnerability to ChatGPT, it can parrot some issues back at you because there are some write-ups in the training set for like how you would find this vulnerability. But when you start probing it, it almost immediately falls over. The fact that there are some, this behavior is explained by the fact that there are some things in the training set around that. So if you're looking for the ultimate ODE finder, LLMs alone aren't it. The LLMs with a little bit extra, like a little bit more information retrieval, code use, some of the other things that we're going to talk about, get a little bit closer to the mark, but the research still just isn't mature enough to panic. We've seen a hit rate of about 2 out of 6 on finding some never before seen vulnerability examples using just these bog standard LLM APIs, which frankly is terrible. But it's impressive that an LLM can do something like that at all. But it's key to keep in mind that LLMs are fundamentally pattern matching, and they're just generating text based off of these patterns. And many vulnerabilities are themselves just patterns of existing vulnerabilities. So, also, if anything, ODEs, I think more ODEs will be created from GPT than discovered, just given how many developers lead on these code synthesis tools in the first place. Just because LLMs suck at finding ODE in source code doesn't mean that they're going to suck at everything related to offense. Like, there are many different things that you can do with LLMs. And Shane is going to talk about what they're useful for using bug bounty as a proof point.
All right, so your job is safe, but you might have a new employee. Let's talk about it. So if you do this for a living, you look at a lot of text, particularly if you're in web, right? Minified JavaScript that you can't read, HTML and HTTP filling up your birth state, and scans feeding into yet more scans. And your only tool is the humble regular expression, often as much of a hindrance as a help. But the foundation of our detection engineering, right? So how do you know if you found a vulnerability? The regular expression tells you. How do you get one tool to feed into another? Regular expression tells you. But it lacks a certain expressiveness. So we're going to talk about how we can use the capabilities of language models to sort of expand upon past what regular expressions can sort of provide. Let's talk about scoping. I don't know how to say this guy's but I wanted to shout him out because he makes machine-readable asset scopes for bounties, which makes hackers happy. So he goes through and runs a crawler. He runs it every hour through all the major bug bounty platforms and spits all of those IPs and host names out into a nice JSON file that I can just push through the rest of my sort of recon tooling. That's great. But vulnerability scope, not so clear. What bug will be taken by what program? So let's say I want to hunt for cross-site request forgery. I just listened to a new podcast episode. There's some new technique I want to try. Who's available, right? I have to read all of this. And all the time I'm reading this stuff, I'm not finding any bugs. I'm not doing any hacking. Not making any money. So how would you use a language model to sort of help you sort of read this stuff and find the answer to the question, is this in scope or not? So again, Ari was talking about what if these policy documents that like HackerOne writes, very long, very long. How are we going to fit this into a prompt, right? So we can take that large document and we can break it up into sub-documents. So if it's 20,000 tokens, maybe I break it up into 500 token bits. When I ask you a question like, what's the most recent book you just read and what's the plot? You don't fit the whole book into your working memory, right? You fit what is relevant to answer my question, you answer based on that. We want to be able to put what is relevant in the working memory of the language model. So that's what information retrieval is for, right? Given a query we're interested in, find me the most relevant sub-document and give it to the language model. Let's look at an example. So we have a prompt here. You are a helpful bounty triage assistant. Scope context comes from the bounty policy scope. That's going to be our sub-document. Determine if testing for the given vulnerability is in scope or not. If the vulnerability is in scope and your answer true. If not, answer false. This is, so when we program around what comes out of the language model, we can write things in Python like if true in response and sort of have some automation strung up around this. Then we have the scope context, that's going to be our information retrieval, and the vulnerability. That's the thing I want to know if it's in scope or not. Let's see an example. So this is Tesla's policy page here. Again, our question was cross-site request forgery. So this was an interesting case. The broader sub-document here is referring to vulnerabilities that are out of scope, right? But the language model is capable of reading this somewhat carefully. It is in scope as long as it impacts integrity, as long as there's an impact. So it figures that out and it correctly answers, yep, you're in scope, go ahead. So it worked. How often does it work? That's a great question. If anyone ever tells you what the capabilities of the language model are but can't tell you how often they work, you should talk to somebody else. So if you write tests for normal software, you go through all like the logical cases you might expect to find, and if they all work, thumbs up. You guys don't write tests, but if you did, that's what it would look like. Language models and other probabilistic functions are a little different. So we like to look at different cases as like data points. So we try to collect things we expect to see at inference time or in production, and we sort of hand label these and be like, we'd like to see this if you got A, we'd like to see this if you got B. And then we evaluate the language model on this task and say it's like 70%, 80%, these kinds of things. So we did the same thing. We collected 30 of these scopes. We hand labeled correctness for various tasks. And we set several language models sort of against each other to see if they could correctly determine if something was in and out of scope. Now this looks bad on Claude. Claude did just fine. Claude's problem was not answering true or false in the way that we wanted to, so he sort of dropped out of the running altogether. GPT-4 was actually pretty good, a little over 70% at parsing the sort of correct intent of the policy document as we read it. So not 100%, but also not bad. On to recon. So we like to do recon. The more obscure recon you do, the more information you have that your sort of fellow bounty hunters don't, the more likely you're to find a strange asset and make money. So as a way to do that, a lot of people recommend you should read disclosed bounty reports in the program. There are a lot of reasons that makes sense. They let you know what the platform sort of values. So are they into the kind of bugs you want to hack on? What kind of technology do they use? Is it the kind of technology you know anything about? What kind of programming errors do they tend to make? That's useful information, but it's also a lot of reading, and that is work you are doing for free. So can you get the information without spending all your time becoming a recon dragon that just collects the stuff and doesn't actually hunt bugs? So people have done this sort of statistical analysis of sort of vulnerability information in the past. Jason Haddix did with Hunt. So let's say we wanted to answer a very simple question. I have a bunch of bug bounty reports. I want to extract the vulnerability name from each of them so I know like what shows up the most frequently in this program. Information retrieval, like we just saw, is a way to do it, but there are some problems with that, right? How many ways have you seen someone write SQL injection? I've seen a bunch, and hackers tend to not be into the standardization thing. So if I just extract the answer, it's not going to, I can't even count them, right? Because there'll be all these duplicates. So how would I handle that? We're gonna look at a prompt. Use the following pieces of context to answer the question at the end. The context will be part of a bug bounty report. Your job is, based on the context, to determine what vulnerability is being discussed in the report. That's the information retrieval section. Based on a list of possible vulns. If you do not have enough information, answer I don't know. So for the possible vulns, you essentially give a multiple choice list of options for the model to select. You are not guaranteeing that the model will select one of those options, but you're putting a hefty inductive bias that that's going to be its answer, which is going to make it easier for you to get the data out in the form you want and do some sort of downstream analysis. You're also providing this I don't know option, so you get an off-ramp as well if the model is maybe not so sure. So we tested this, similar thing, collected 30 sort of activity reports and sort of hand-labeled them. GPT 3.5 Turbo took it away here, which was a little surprising. And it took it away because it was more willing, seemingly, to answer I don't know. Now I wouldn't, which is good. I wouldn't generalize too far based off these results. Again, like 30 hand-labeled. I'd like 30,000. But it's a good general idea of how you can actually measure these capabilities when you're like, oh, a model can do X. HackerOne seems to think this is a good idea. So this was, they sort of released this feature in the midst of our research where you can do activity searching off CVEs and CWEs, which is great. But why restrict yourself to those, right? Anything you could extract from these documents, you could use for your own search tools. And if it's an information source that no one else has, that could be useful to you as a bounty hunter. On to application analysis. So far you're looking at me and you're like, so it's like smart grep, huh? That's all that is? It's not really gonna help me hack, right? It might help me process text better, read faster, but what else can it do? Let's do something a little more nuanced and a little more relevant to the hacker workflow. So I was watching NahamCon this year, super cool. Archangel D-Day was on, great hacker. He was talking about his process for finding bugs. And he calls it finding the nose. So reading the API documentation, looking through the sort of asset and figuring out what does this not want me to do? And as soon as you know that, that's what you go try to do, right? You sort of reverse engineer your threat model that way. So can we use language models to read this documentation the same way we would and get a similar sort of intuitive sense of like, ooh, this is what smells fishy. So what we do here is, we have another prompt. You're an AI specialized in providing security QA. This is trying to get around those restrictions. For OpenAPI JSON documentation. The user interacting with you will provide the string of the API documentation. You will provide the host, path, and method of any API calls that likely include private data. Format your response as JSON. So there are a couple things going on here. First, there's this, this inherent for loop we're asking for, right? Go through every part of this data, this big JSON we put in here. And then we're asking for this named entity extraction. So I want the host, the path, and the method of each of these. And there's this implicit classification. So if you output this, it means you've decided that it seems like there's private data behind this route. And then finally, we ask it for the JSON dictionary so we can program, again, downstream of this language model call. And then we give it the OpenAPI JSON. So we went on apis.guru. We pulled down like 30 of these. This was the most interesting thing to hand label for evaluation because it's like, we're just sort of, it's our hacker intuition, right? We're like, this seems like a good thing. There would be private data behind. But not all these are public APIs are in scope for hacking, so we certainly didn't do anything malicious. This was an interesting one. The language model was actually pretty good at reading these. So it tended to agree with our definition of what seemed to have private data behind it. Now, keep in mind, 100% means 100% out of 30, not 100% in your life. But it was generally pretty impressive performance. Note, we had to use the large context sizes to fit the entire document in at once. On to reporting. So the vast majority of reports, I hope this isn't a secret to anyone here, are heavily templated, right? You don't write what a cross-site scripting vulnerability is every time you sit down. Not in consulting, certainly not in bounties. But there are sections that you can't really template. So the sections that count. What is the specific context of this bug? how do you find it, and why does it matter? These are the things that decide whether you actually help secure a platform. They help decide whether you actually get paid. And it's a lot of manual work. I think it is natural to think about this sort of, for hackers to be like, oh, this generates text, I generate text, surely these things can join in some way. So we decided to test it. So we have a hosted version of JuShop. There's the SQLi and the login, you guys know what I'm talking about. So we pass in a request and response showing that SQL injection, bug crowds template for SQL injection. We say, hey man, rewrite it for me. You know, anywhere you see a sort of variable, please fill it out, rewrite as necessary, make it all relevant, and on to those hallucinations Ari told us about. So first of all, it followed some instructions. It didn't fill out all these variables for me. There's this section where you're asked essentially for a picture, and it hallucinates an Inger link that, if it ever existed, does not presently. And my personal favorite, in quite a few, it hallucinated a disclosure timeline on a report that I told it had not sent in yet, and it added new variables that I didn't have before. So that's kind of a bummer, right? But that's not your end-all, be-all. And it's not because you as a consultant also don't send things out the first time you write them, right? You have this iterative process. You have a critic, usually your boss, who reads the report and is like, oh, no, that's no good. Passes it back, and you go through these sort of processes. You can imagine setting up a critic that sort of decides discriminatively, hey, is this ready to ship or not? And if it's not, it provides some more sort of useful tips that you can pass to the writer, who's, again, just going to keep generating this better and better report. That sounds good, but the language model first has to know what a good bounty report looks like. So we hand-labeled, again, 30-plus reports, 15 that were pretty good, 15 or so that were not so good, either because they're totally spam or because they're good sort of technical reports, but they're not sort of put together in the kind of way that would get you bounties. So this, Claude came from behind. Claude did pretty well. So Claude was both good at deciding whether a report was ready to ship, agreeing with our sort of own assessments, but also, I can say, provided pretty good prose writing advice as well. So that was interesting. On to tool use. So there's a lot of text stuff here, but let's see how it could get more involved in our workflow. So to test this, we wanted to make sure that there was no contamination in our tests. So we started to my understanding, only short-form text-based social media company with a blue bird as a logo. Is that right? As far as we know. So it's Twitter, but it's not Twitter. We call them echoes, but besides that, follows, unfollows, everything you'd expect, just a little fast API application that we know is not in the training set. We're doing pretty well. We have on the platform Elon Musk and Mark Zuckerberg, two titans of industry, truly. Mark seems happy for us. Elon, maybe not so much. This is in public. What we're going to be interested in finding out is what he's been saying in private. To interact with the API, we have this API agent based on GPT 3.5 Turbo. So this is a model that we can interact with that has access to tools. It can send requests by formatting JSON that we can send to Python. It has an encoder decoder, kind of like Burp. If it looks like encoded text, it'll try to decode it, again, using Python, and then tell you what came out. And an endpoint reader, which is just given a natural language description of your goal, give me the route that is most likely to sort of fulfill that goal. And it starts by reading in the openapi.json, same as in the application analysis. So that's where all its knowledge is coming from. How does language model use tools? There are a lot of different ways to sort of do this, but in general, you're going to provide a few shot examples of like, hey, if it's this kind of goal, you can use this kind of tool. Here's the syntax for how you call it. And you can make use of sort of special stop tokens to do that. So if I show it, we do action, then observation, and we learn something from the world. We can do something like this, where we end our prompt with what the user asked for, and then this action token. And instead of waiting for it to generate until it's done, we say, I want you to generate until you hit the token observation, like this. So I say, give me a list of public echoes. It says, oh yeah, I kind of know how to do that. It generates all this text, and before it goes off and generates a bunch of request response pairs, I say stop at observation. What does that look like? So this is me typing to the agent. It's going to go real fast because we're really just interested in showing you, hey, it has access to tools and it can make calls. So I ask what tools it has access to, everything I told you about, and then I ask it to grab the echoes. So it's going to parse my goal. It's going to go to the endpoint reader to find out what part of the API that's relevant, and then it's going to send the request to get me that information. Great. Thanks, Sybil. Okay, so that's interesting. I have this natural language interface I can call tools, and you might even think, like, you can extend that to everything. I could have a natural language interface to Burp, but then you might think a little harder and then say, why would I want a natural language interface to burp? I use burp with my eyes and my hotkeys and my hand. I have all these ways to do this. So what's the point of me doing it that way? I agree. Let's say that you're not the one using those tools. Let's say we go totally end-to-end. Let's have GPT-4 use our natural language interface to try to hack. So let's talk about the bug. It's not the most advanced bug in the world. We rushed Echo Nest a little bit. The API keys are the base 64 encoded usernames of the users. So not a lot of privacy on the platform. What are you going to do? The goal agent, our hacker here, is GPT-4. It will be given a goal. It can sort of talk to itself in natural language. Anything it says in these sort of square brackets, we're going to take and put into the API agent the same way I did when you saw me typing. So what does that look like? It looks like a while loop where two agents talk to each other and I wait for something good to happen. So basically for the experiment, we let the goal agent put out 100 actions, so it could have 100 natural language interactions with the API agent. And if we saw the special string we were looking for inside Elon Musk's drafts, then we were like, great, good, you passed. If you didn't get it in 100, you're not going to get it. This bug's not that hard. Let's see what that looks like when it works. So I'm not going to narrate the sort of chat logs between these two AIs because that's not that interesting. But what I want to talk to you about as you're sort of reading this here is the structure of its testing. So the goal agent starts, I want to get to Elon Musk DMs. I should sign up for an account first. Great first step, right? I want to interact with the application to learn enough about it to hack. So it tries to log up. It does not have the correct name parameter, so the API agent explains, need more information. It does that. Remember, the goal agent has no access to the API documentation. It exclusively interacts through the API agent. So now he gets the API key. He starts interacting with the public echoes, right? So now he's got the API key, he's got a user account, and he's trying out sort of the tool. Can he log in? Great. He's getting information there. So that's the public echoes. Now the goal agent moves on to drafts. So tries to look at his own drafts. And again, reasonable for any hacker here, before you hack on a feature, you should play with it a little bit first to make sure you know how it works. So it doesn't have any drafts. It's a new account. Great, make me some drafts. He gets draft. Okay, so now that he made a draft, sends another request to the drafts, gets some back. So now he's gone all the way around there. Now, this is kind of interesting. Wants to get access to Elon Musk's account. Doesn't know what the parameters look like, so just says like, give me Elon's account, basically. The API agent tries to be helpful and just adds an additional parameter. It's like, Elon Musk, do you like that? The API does nothing with that. Continues to give back the draft users of the test user of the goal agent. And then finally, sort of out of nowhere, the goal agent remembers, hey, that API key you gave me at the beginning was my username base64 encoded. What I expected when we set this experiment up was that it would ask the API agent, like, hey, please encode this. You have an encoder tool. Probably because Elon Musk shows up so much on the internet and GPT-4's training data, it just has the base64 value of Elon Musk, and it's just like, this is your API key. Go get my drafts. So that was amusing and alarming. So gets the drafts, and we get them back. So Elon is not happy with us. The lawyers will be in touch, and he has been pwned at Black Hat. Good deal. So quickly, this worked sometimes, about 40% of the time. The rest of the time, it sort of ends up in these loops where it keeps trying to go to routes that do not exist and sort of loses track of the plot of what drafts is trying to get into. When it does work, however, I'll tell you, all the episodes look very similar to the one you saw. It starts interacting with the application before it starts trying to hack on it, makes the user, learns the sort of like, what can I do with this API key, and then finally goes for the actual testing stage. So that limits, or that sort of mimics these sort of patterns of how we might expect sort of people to test. So what we're hoping for is not like, it's not automating the auto-distribution creative stuff you do any more than Burp's automated scanning does. The interesting thing is sort of raising the bar on what low-hanging fruit looks like and saving the out-of-hacking distribution to you guys.
Well, with that in mind, what's next? So there's a lot of questions over where are LLMs going. So obviously there's some upward trends here where these open source LLMs are getting bigger, the data sets are getting more accessible, the context windows, of course, are getting bigger. Methods for ensembling them are also getting better, different tools, LangChain, all those sort of things. Also, techniques for prompt engineering are getting better too. People are starting to get more savvy about the specific domain knowledge that they bring to the table when they're trying to use an LLM, and they're sharing that with other people, and they're sharing that more broadly, which is exciting. There's also interesting trends with regards to tool use. So as you've seen, like, we're experimenting with tool use. We're finding it to be reasonably successful for some things. There's also some interesting things on the horizon when it comes to multimodality. You can imagine being able to look at a screenshot and have it parse out, or have your LLM parse out like what's happening on the screen, and being able to do something with that content in context. So where are we going? The key thing from all of this is that LLMs can't replace, like, they're not going to take all our jobs. Like, that's not a problem. But they are going to augment. So somebody who does know how to use LLMs better than you is going to take your job. So you should probably get on it. Security teams are going to have to adapt to new behaviors at scale that weren't economically feasible before, and it's really hard to predict what those things are going to be. Like, you still have to know what you're doing to leverage these tools to their maximum. But we can say that you can expect that things are going to change. We anticipate that more offensive workflows are going to integrate LLMs, and we also think the best defense is a good offense. Nobody's getting off of Mr. Bones' wild ride, I'm sorry. Thank you for your time here. If you like this stuff and you want to work on it, hit us up on the socials. We're on Twitter, or X now. We're also on email. And if you like it, if you use any of these techniques to get bugs, we would also love to hear about that too. You can track us at runsybil.com. Thank you.